My name is Laika Bisonatokmo, and now let's have a short recap about what our previous topic was all about. Anyone who wants to participate? Yes, that's right. And now let's have a short activity.
Let's have a short activity called a drill. Review of our previous lesson. Before we proceed with our lesson for today, I have prepared a game. I have here jumbled words, and let's see how you are going to unlock the hidden word. And now, start your game. Alright, you got all the words correctly. What do you think these words are? And now, let's proceed to the answer. First, we have the hydraulic, and the second one is the velocity. The third one is the principles. The fourth one is hydrogeology. And the fifth one, which is the last one, is the purpose.
And now let's proceed to our next lesson, which is the Chezy and Darcy equation.
Before anything else, what do you think our lesson for today? Yes, our lesson for today is the Chezy and Darcy equation.
Objective. At the end of the lesson, the students will be able to define the Chezy and Darcy equation, determine the coefficient of friction. Students will understand the principles behind the Chezy and Darcy equation.
Yes, the Chezy and Darcy equation are fundamental equations used in fluid mechanics to describe different types of flow, open channel flow, and flow through porous media, respectively. The Chezy equation, named after the French engineer Anton Chezy, is used to describe the velocity of flow in an open channel. The equation relates the velocity of flow to the properties of the fluid, the geometry of the channel, and the roughness of the channel walls. It is particularly useful in hydraulic engineering for designing and analyzing open channel flow systems such as rivers, canals, and stormwater drains. Now, principles behind the Chezy equation include velocity of flow. The velocity of flow, or V, is influenced by factors such as the slope of the channel and the hydraulic radius that relate to the shape of the channel. And the roughness of the channel walls is higher than slopes, and larger hydraulic radius generally results in higher flow velocities. Next, Chezy coefficient, which is represented in C. The Chezy coefficient is an empirical constant that accounts for the roughness of the channel walls and other hydraulic factors. It is determined experimentally based on the characteristic flow and the material channel. Next, hydraulic radius, or R. The hydraulic radius is the ratio of the cross-sectional area of flow to the weighted perimeter. It represents the effective flow area per unit of weighted perimeter and is a measure of the coefficient of flow. Last, slope of the channel. The slope of the channel, often denotes by S, represents the change in elevation of the channel bed over a certain distance. It drives the flow of water down to the channel due to the gravity.
In this lesson, we will formulate the Chezy equation and compare it to the Darcy-Weisbach equation. Antoine de Chezy was a French hydraulic engineer who was commissioned to design a water supply system using a nearby river, the Yvette River. He was set to determine the relationship between the channel geometry and the river velocity. However, there was no literature at the time that gave this relationship, so he made his own analysis. In his analysis, he found that the velocity was proportional to the square root of the hydraulic radius and the channel slope. His formulation gave us what we now call the Chezy equation. In this equation, the term C is a factor of proportionality that relates or changes from channel to channel. The S value is the longitudinal slope, which we will discuss later in this section, and the R value is the hydraulic radius, which we already know is the ratio of the flow area to its wetted perimeter.
And now, let's proceed to the Darcy equation. The Darcy equation, named after the French engineer Henri Darcy, describes the flow of fluids through porous media, such as soil, sand, or rock. It is used in various fields, including the hydrogeology, petroleum engineering, and soil mechanics, to understand and predict fluid flow through porous materials. Principles behind Darcy equation include flow through porous media. In porous media, fluid flow occurs through interconnected void spaces or pores within the material. The Darcy equation quantifies this flow in terms of the velocity of flow, the hydraulic gradient, and the properties of the porous medium. Velocity of flow is similar to the Chezy equation. The Darcy equation relates the velocity of flow, which is v, to hydraulic factors. However, in this context, it represents the velocity of flow through the porous medium. Next, hydraulic gradient. The hydraulic gradient represents the driving force for flow through the porous media. It is defined as the change in hydraulic head, which is pressure head plus elevation head, per unit distance along the flow path. Next, hydraulic conductivity. It is a property of the porous medium that characterizes its ability to transmit fluid, and it is dependent on factors such as porosity of materials and the size and connectivity of the pore spaces. Now, the last one, cross-sectional area and length. This parameter represents the dimension of the porous medium through which the fluid is flowing.
In order to understand how the Chezy equation works and relates to friction, let's look at how the Darcy-Weisbach equation applies on open channel flow. Let's consider a steady, uniform open channel with a constant cross-section, as shown in the figure. If we want to apply the energy equation for steady uniform flow, we can set our inlet control surface on the left as number 1 and our outlet control surface on the right as number 2. In this system, we have no pumps or turbines, so we can eliminate those terms from the equation. Also, remember that for channels with little to no vertical acceleration, we can take the change in pressure along the vertical axis as equal to a hydrostatic change in pressure. This means that at any 2 points in the control surfaces, the pressures should be the same and there should be no variation between the upstream pressure and the downstream pressure. This means that we can cancel out the pressure from this equation. Similarly, if our cross-section is uniform, then there should be no change in velocity from the upstream control surface to the downstream control surface, so we can cancel out the velocity from this term. This leaves us with an equation of head loss as a function of the elevations of the control surfaces. We can call the change in elevations delta z. In the image, which I got from Hibbler's book, they call it delta y. The right triangle formed between the datum and the channel bottom can be analyzed as follows. The change in elevation delta z can be taken to be equal to the length of the channel bottom times the sine of the angle of inclination of the channel bottom. We can define the longitudinal slope S, or S naught in the figure, as the change between the elevation and the horizontal direction, delta z over delta x. Looking at this right triangle, we see that delta z over delta x is also equal to the tangent of the angle of inclination.
And now, let's have more understanding about the Chezy and Darcy. The Chezy and Darcy equation both involve fluid flow, which is right, but they don't directly incorporate a coefficient of friction, like you might find in equation related to solid body friction. Instead, they account for the effects of friction through other parameters, which is right. Okay, let's synthesize our topic. In both cases, introducing the coefficient of friction modifies the equation to account for the additional losses or resistance experienced by the fluid. Due to frictional effects, this modification would provide a more comprehensive representation of fluid flow behavior in open channels through porous media, which is the connectedness of the Chezy and Darcy equation. Okay, everyone, to know if you are truly understand our lesson, we will have a short quiz. Get ready.
Thank you, and that's all for our lesson for today.